start the class. So we are still into history, but we are going over astronomy as well. So last time we talked about the tapestry of Bayeux, and definitively in a test, right? It was the first recorded time. It was the first time where the comet was recorded. So it was recorded in a tapestry, and you can see it here. So if you like history, especially the history of England is very, very interesting. So it's a very famous battle. It's called the Hastings Battle, when not France, it's really the Duke of Normandy invaded England and took over England. And the king was Harold II. And to his credit, his troops, his army was exhausted because he had to fight his own brother after the death of his father, and he had to fight the Norwegian as well. And then back then you didn't have tanks, they had to go by feet mostly and horses to meet the French. So the name of the Duke was William the Conqueror. And if you like French, interestingly, William translates as Guillaume. Guillaume le Conquérant. Don't ask me why Guillaume translates as William, but that's what happens. Okay, so this comet here comes back every 76 years, and it was Edmund Halley who predicted for the first time in 1682 that comet comes back every 76 years. Okay, and that's when he asked his friend Newton, how come? What's happening there? And that's when Newton said, I figured this out 20 years ago. It's because of gravity, right? To explain gravity, what gravity was. And that's when Edmund Halley, paid for the publication of the most famous book in science, which is called Principia. Okay, so if you have a question about that, it's called Principia. Very famous. So anyway, he predicted that it will come back in another 76 years. He was dead by now, but they named the comet after him. So it's called Halley Comet. Okay, and you can go also on my website here. I used to have a website. That same comet was seen in 1577 by Tycho Brahe as well. So same comet. And the first time they had a drawing of a comet was in 1531. 51. Oh, I'm tired today. 1531. And it was the first time that you had this very nice illustration. It's a German astronomer here. So if you like art, and he's the one who understood for the first time that when a comet passed by the sun, its tail, you see the tail of the comet will be pushed away by the sun. So he didn't understand that was the solar wind pushing it away, but he saw that. He saw that the tail was always pushed away. So it's an amazing illustration. If you are into art, it's also very famous. Okay, and just want to show you a very short video, but a very nice one about Halley Comet. And there is no sound? Yes, there is sound.
Halley's most famous comet, captured by Jupiter into a short period orbit 200,000 years ago. Since then, Halley has returned to our skies, on average, once every 76 years. Halley's ellipse brings it from beyond the orbit of Neptune, when farthest from the Sun, to within the orbit of Venus, when closest to the Sun. At its last appearance, Halley moved through our skies like this, on its way to the Sun late in 1985, and back out in early 86. Halley appeared in medieval skies when in 1066 the Normans conquered England. This from the Bayeux Tapestry. Halley was the star of Bethlehem, Giotto's fresco. He'd seen the comet in 1301. That comets are periodic in return was predicted by Edmund Halley. He saw the comet in 1682. Halley's comet, as it became, was first photographed on the return of 1910. And when it reappeared in the 80s, the space age had a welcome. An international armada headed for a rendezvous. 2 probes were Russian, 2 Japanese, and 1, named Giotto after the painter, European. Giotto flew closest of all, right through Halley's coma, the halo of gas and dust that vented from an icy nucleus, 16 kilometers by 9.
So it's short, but it's very nice. It's a very nice video, and I lost my here. Okay, so now I'm gonna stick to the PDF. Okay, so Halley comet comes from the Kuiper belt, and it takes 76 years for one cycle. Okay, and what's happening when it's going to be close to the sun? It's going to go really fast. So last time we had like a small window, 1985, 1986, to observe that comet, and then it takes forever to complete the cycle. So next time it will come will be 2061. So it's going to go really fast, and then it takes its time. It's very slow. Okay, and that was predicted by Kepler. Okay, it's going to follow an ellipse, very flat ellipse that you can describe mathematically, and then it was proven by Newton using the calculus, right? It's because here the force of gravity, the force due to gravity is stronger because it's closer, so it's going to pull on it stronger, and then it gets weaker, so it's going to slow down, speed up, and then slow down. Okay, so then we move in history and we get to William Herschel. So also very, very famous in astronomy. Very interesting story. So I don't remember all the details about his life, but it's super interesting. There was a YouTube video about his life. So again, there was the war again in Europe, like as usual. There is always war in Europe, and it was a 7 years war. So it was not about Protestant and Catholics like the 30 Years War. It was about Germany and I don't know what. Germany was at war. So he had to flee Germany, right? His parents were staying in Germany. They had to flee Germany to find opportunities, and he went to England. So his dad was a musician, but not a great musician. He was playing oboe. You know oboe? Right? He was playing for the troops. He was playing for the army to cheer them up. That's what they used to do at the time. You had musicians just to cheer everyone up when they will go to war. So he will play oboe and move to England, and then he became a great musician. He was playing organ, so he became an organist, right? Very, very good. So he went from nothing, so he didn't have a lot of money, and then he made his way all the way up because his skills were recognized. And he brought with him his sister, Caroline. So also very interesting story because at the time, well, women were from not a very wealthy family. Either she had to end up as a maid or she had to be married to someone older and richer if she was beautiful. But if she was not beautiful, there was not much choice. She could go to a convent, she could become a sister, or she had to work as a maid. So, because he really liked his sister, he saved her from that life. and together they started to work in astronomy. So he became very passionate about astronomy. So then he gave up his love for music, and then he got into astronomy, and he is the first one to build a very, very large reflecting telescope. And because it was so expensive, right, to make those lenses, and mirrors. So at the time, you see the mirrors were made with some kind of metal that you have to curve, right, just to the right size, to the right shape. Okay, you have to make a huge mirror, and he did it on his own with the help of his sister and a little team that he hired. So he built the first giant telescope in Europe, in the world, right? The first reflecting telescope, and he discovered Uranus. So that was the first planet discovered at the time, right? Uranus. He discovered Uranus, and he got the money from the king of the time, George III. Okay, so the king was his patron. So the king gave him like a pension, give him money. So when he discovered Uranus, he called that planet the king star, the Georgian star named after George III. But of course, the French didn't like the English people, so then they changed the name to Uranus, right? They didn't like that it was named after an English king, so it didn't go very well. But for a while, it was called Georgian Star, okay, named after the King George III, and he was called the King Astronomer. So he built the largest telescope ever at the time. You can see that here. And then he asked more money to build an even bigger telescope. But that telescope didn't go well. But he could not say it because he will upset the king. The king didn't want his money to go to waste. So what he will do, he will go to the small telescope, he will make a discovery, and then he will run to the bigger telescope and say, "Oh, I made a discovery." So the king will not get upset. And because he was very kind to his sister Caroline, he got her a pension as well to make sure that she will never be in need, right? So he saved his sister in a way. And she became also a very good astronomer. She will catalog everything they saw. And I think she was the first woman, yes, to get a gold medal from the Royal Astronomical Society. So the first woman to be recognized in history in astronomy. So his history is very interesting because he started not to be wealthy, and then he followed his passion, went to be a musician, very famous musician, and then a very famous astronomer that we'll remember. And then he worked for the king. So at the time, it was really possible to go from nothing to all the way to the top. So I have a very nice video, but I just have to find it. Herschel.
Making large mirrors exactly the right shape is far too difficult. It will be a century after Newton before a new pioneer picks up his revolutionary design and transforms it. That man is musician and amateur astronomer William Herschel. Herschel has great ambitions. He wants to use a larger version of Newton's reflector to see further into space than anyone before. Now, Herschel is a musician, astronomer. He's a clarinet player, he's an impresario, he's a composer. But his real passion isn't music, it's astronomy. Herschel wants to look anew at the night sky. He wants to look beyond the planets to the stars, and to see the very faintest stars invisible to other telescopes of the day. Herschel needs big mirrors.
He builds telescopes that are bigger than other people's because he realizes that the wider his aperture, the more light he can collect, the further he can see into space.
Making large curved mirrors, though, is still a major technical challenge in Herschel's day. Glass mirrors have not yet been invented. Mirrors are still made of metal. So, working in his basement, Herschel casts discs of a metal called speculum, a special mixture of molten tin and copper. These will become his mirrors.
We don't know what the neighbours thought of this mad fiddler burning the entire room.
Plastic metal discs is just the first step. To become mirrors, the cooled flat discs need a shiny curved surface. Herschel painstakingly grinds and polishes the metal discs by hand into the precise shape needed to form an image.
This is the reflecting mirror, the most precious component in the telescope, made in metal by William Herschel himself, made by hand. He was like a craftsman, making something which required manual skill as well as intellectual effort.
This telescope, over 200 years ago, makes a revolutionary discovery.
Or perhaps a comet.
In 1781, Herschel peers night after night into the heavens. At his side, his sister Caroline.
Following Delta Tauri,
She records all their observations and will become a prominent astronomer herself.
Her observations were critical.
She was one of his true secret weapons. Then, on March 13th, Herschel sees an object through his telescope that they have never recorded before. A very faint star that seems to move against the backdrop of the other stars. This wandering star is a brand new planet, Uranus.
The planets have been identified since the dawn of written astronomy. And then suddenly you have this clarinet player, with homemade telescopes in his back garden being discovered another one. The thing is utterly astonishing.
Uranus, with its own set of rings, is the size of 63 Earths. But no one has identified it before because it is barely visible with the naked eye. 1,900 million miles from the Sun, it is twice as far from the Sun as Saturn, until then the furthest known planet. Overnight, Herschel doubles the size of the solar system. The discovery sparks a frenzied hunt for planets. It is a quest that the world's most sophisticated telescopes continue to this day.
So I think it's a very nice story because he didn't really had the college education. He was like first he was playing music, for the army, and then he got into astronomy and he discovered the Uranus. Since the Greek, no other planet was discovered, and then he became the astronomer of the cake. So it's a very nice story. Okay, I think I have a picture also. Here. You have a picture of his huge telescope. So again, remember, for a test or for the final, you have reflecting telescope and you have refracting telescope. Refracting telescope are cheaper, and it was improved by Galileo. But reflecting telescope, that's the one we use today, and it was for the first time it was developed by Newton. Who he did that? He did that like just like this, right? Out of the blues, because he was a genius. So anyway, that will be William Herschel. Now today there is a telescope named after William Herschel, and it's in Spain, in the Canaries Island. This one. Okay, so 4.2 meters William Herschel telescope, Palma in the Canary Islands, Spain, 1987. So if you are interested, you can go into that and learn more about it. Right? So it's named after William Herschel, and this is his sister Caroline. So not only that, he was also very curious about science, And remember, if I ask you, Newton, he was also into optics, right? He's the one who find out that you can divide white light from the sun into its components, wavelength, right? So here, these are the visible light, but you also have infrared beyond red. And then here, beyond blue, you have the UV light that we get on Earth. But at the time, they only knew about the rainbow here. And then I don't know how he came to think about it, but he got the idea to do the same experiment as Newton, but then he used a thermometer. So he used a thermometer here to measure the temperature. So through all those colors, there is no change in temperature. And then he placed that thermometer just beyond the red. And all of a sudden, the temperature increased. So he just discovered infrared. So what is infrared? Is the heat. So when you go outside, you feel the heat from the sun. These are infrared light. You know, nowadays we use infrared light for therapy. You know, they say it's gonna fix and repair mitochondria. So anyway, he's the one who discovered infrared just using a thermometer. Okay, so we are called black body. That means that we are burning fuel and we are emitting radiation. So what kind of radiation we are emitting? We are emitting infrared. So if I turn off the light here and everything is dark, you will be all shining in infrared. And I could see you if I have those special sensors that firefighters they have. You know, firefighters when they want to save people in the smoke, you know, you cannot see anything with the smoke, but if you have those special sight, right, goggles, those special infrared goggles, then you can see people shining. And if you know what type of radiation we are emitting, you know our temperature. So there is a connection between the radiation that we emit and the temperature. And we're going to see that for stars as well. So for the sun, if we know the color of the sun, it's a white star, then we can find its temperature. Same thing with us, right? So if we can see what type of infrared we are emitting, it's a heat wave, we know our temperature. So if you run a fever, the infrared will change, the radiation will change. So anyway, if you have any question, let me know. But he's the one who discovered infrared. I don't know how he came up with this idea to have a thermometer here run through all those colors, and he placed it here just after the red, and he discovered infrared heat, which is heat wave. Okay, so now we are skipping to general relativity. And no, it says I have to take a break because there was a video that I forgot to show you. So that's the very famous video. So if I ask you, you know, if you take a book, for example, and a piece of paper on the moon, okay, you drop them from the same height, they will reach the ground at the same time. And that was from Galileo. So regardless of their mass, okay, if the objects are acted upon by gravity, the acceleration will be the same and they reach the ground at the same time. He was able to show that using these devices called inclined plane. Remember that? And he was able to dilute gravity. So he did all those experiments. So when they went to the moon, 1969, around then, so I don't know exactly when they did that experiment, but they were able to show that experiment, right? So I just wanted to show you that. I, so it's a very famous video, but you can do that also on Earth. The idea, so that was done by Brian Cox. Here, he's very famous. You can find many videos on YouTube. Okay, he explained particle physics, string theory. He's a very good public speakers. So anyway, he's gonna show you the same experiment but on Earth. So there is this huge container, and they are able to remove the air, right? So if you remove the air, there is no more air resistance, so you can do exactly the same experiment. I'm gonna speed up. I'm gonna speed up.
Space and how emphasized lead for fire. And it is the world's biggest vacuum chamber. It's used in conditions of outer space. And it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, strongest material to build a vacuum chamber out of. So they built out a concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now, in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So, in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air chamber. We dropped 2 millitorr in the last 30 minutes. But once it's complete, there's a near perfect vacuum inside.
61 flow fan with 10% over. Station 1, go for drop. TCD 30-1, pressure set point 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4, 2, 1, release.
Exactly what I'm going to say. Exactly right. Nothing. That's just brilliant. Isaac Newton would say that the ball and the feather fall because there's a force pulling them down, gravity. But Einstein imagined the scene very differently. The happiest thought of his life was this: the reason the bowling ball and fall together is because they're not falling. They're standing still. There is no force acting on them at all. He reasoned that if you couldn't see the background, there'd be no way of knowing the ball or the feathers were being accelerated towards the earth. So he concluded they weren't.
So it's a nice introduction to general relativity. Okay, so Newton. Okay, it's Newton who explained using the force of gravity. Why do they fall at the same rate? Why do they have the same acceleration? And it was Galileo before him who was able to show, doing experiment, that this is the way. it should be without doing the math. We just did the experiment. And then came Einstein, put everything upside down and says gravity is just an approximation. That's not what's really happening. There is no such thing as the force of gravity. It's because the space itself is curved. So I will explain, but it's just an introduction. So imagine the genius of Galileo and Newton. So when that happened, Apollo 15, 1971, that's when they did the experiment. Here you have the mass of the hammer and the mass of the feather. Unless you believe that we didn't go to the moon and this is all fake. Okay, so 1905, you have Einstein. Okay, he was a patent, a clerk patent. Okay, he was not even a very good student. He was not really good at math. And he only liked to study what really passionate him. Okay, so he was very passionate about electromagnetism, force at a distance. And then in 1905, he published this amazing paper, several papers. One of them was about special relativity. So special relativity talks about light. So it says, for example, if I was able to go as fast as the speed of light, and I leave the earth and then I come back, your time will have gone faster than mine. Okay, if I go as fast as light and I come back, my time will not have changed. I will be the same age and you will have aged, right? So it's a relativity for time, also for distance. So if I was able to go really fast and you look at me, you see me as I will be shrinking, right? My size here, the horizontal size will get smaller. Okay, it's very strange, but it was proven. So if you go really fast, the time slows down and the size changes relative to another frame of reference. So that was special relativity. And years later, it's like 10 years later, 10 years later, he developed general relativity, saying that Einstein is wrong, that it's just an approximation, that the reason why, for example, the Earth goes around the Sun, so this is in 2D, because 3D it's hard to show you, but imagine space around you. It's some kind of stuff. It's like rubbery stuff. You cannot see it with your eyes, you cannot sense it with your hand, but it's all around you. Okay, so it's like a trampoline in 3D. So let's say it's in 2D because it's easier. So space is made of rubbery material. And if you have something massive enough, it's going to curve that fabric, okay, the fabric of space time. And if you have something like the Earth, it's going to be trapped in some of the curve made by the sun, and that's why it's going to keep orbiting the sun. Okay, so this is the idea behind general relativity. So I'm going to show you. Okay, so imagine how it works. To imagine how it works, you have a wishing well. So sometimes you find that in the mall. So you're gonna put a penny here, and the penny goes around and around and around and around. And because you still have friction, at the end it will go in the well. But if there is no friction, the penny will keep going around and around and around forever. So likewise, if you have the sun, it's going to curve that trampoline net, and the earth, right, it has an initial velocity, initial speed. It will go around forever because it's trapped into that curve. If you have something very dense and very heavy and very small, then you get a black hole. That means the curve is so deep that it never ends. And we don't know what's happening inside the black hole, but that's what a black hole is. Okay. I don't know if I have another picture here. See, this is the sun. So that was the experiment that was able to show that, but I'm just showing you the principle. So that I went to the Frost Museum. I took my nephew, so I don't know if you see it, but they had this model to explain. So you have two heavy objects here, curving space-time fabric, and you give momentum to little marble, and the marble will start to spin around to orbit those two masses. If there is no friction, they will do it forever. So that's the idea. I don't know if I have a... Okay, that's another explanation. So that's from the University of Tokyo.
So what's going on here is that here's the space that is warped towards the center. So that's the idea of the warped space. And if you throw a ball around it, then none of them actually go straight, as you can see. It bends around and goes in a curved motion. So that's the idea of this Keplerian motion of planets around the sun. Sun actually warps space. And that's why things don't go straight anymore and ends up orbiting around the sun. But in some sense, that being pulled by the sun by force of gravity is an illusion. Everything is actually going straight. But space itself is curved. That's why it looks like everyone is undergoing this elliptical motion around the sun.
Okay, so what Einstein said is that gravity, as described by Newton as a force at a distance, is just an approximation. But that approximation is enough to go to the moon, is enough to send spacecraft in space, right? You don't need general relativity. So general relativity is extremely complex. Even Einstein had a hard time with it to develop everything in math because you have to use the math, right? You have to use equations to develop and predict what's going to happen, what's happening, the law of nature. So he had to ask help from mathematicians to develop his theory because it's so complex. And I told you that most of the time the math is not that hard. Like Kepler's law uses only algebra, but general relativity uses tensors. It's extremely complicated. So, but you only need it. You only need it when you're gonna deal with black holes, right? When you're gonna deal with gravitational waves. If you want to send a spacecraft somewhere, you don't need that. You can use something more simplified, which is Newton's law of gravitation. So he's a professor and he's training other future professors, and he shows what they could use for their students so they have an understanding of what general relativity is. So I'm going to speed up. Okay, I just want to show you the idea. I'm going to speed up 20%. If it's too fast, just let me know.
Is that matter than space? So put mass in a place in space, it warps space-time, and objects are not feeling a force of gravity, they're just following the natural curvature. And so this is a sheet of lycra. Where do you get this? It's my old bike shorts. There's literally a spandex.com. You can get a sheet like this if you buy the sale stuff, so you don't care what it looks like, right? For like $20, maybe less, depending on the sale. And so you put matter and it works space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that...
Do you see how those two objects are attracted to each other? So the reason why we are glued to the earth is not because gravity is pulling on us, it's because the space around you that you cannot see with your eyes is pushing you down. Okay, so there is no force at a distance. So if I step on the table and I just step out here, I'm gonna fall. I'm falling not because gravity is pulling on me, but because space itself, which is a 3D rubber, is pushing on me. And you can see that very well in 2D. If you just place them on the rubber sheet, they're gonna be pushed by the rubber together. That's the force due to gravity that says two masses are attracted to each other. So it's very easy to understand conceptually. Of course, it's very hard when you get to the equations.
That's Einstein's picture of gravity. Objects work space-time, feel like curvature, move according. And yeah, more mass. Right there. Yeah, more mass is going to bend space-time more. And so if you have positive power, you're going to respond to that, right? And so you put something there, that was attracted. Now, in reality, that big mass would feel the working of space-time like a marble too, right? It would move a little bit. We usually ignore that. You know, if the Earth makes the sun move a little bit, but it's so small we can ignore it. The moon makes the Earth kind of wobble around and point 3/4 away from the center of the Earth. We usually don't account for that when we're looking at satellite motion. Well, instead of just letting go of one, what if I give it a sideways push? Now it orbits. Now it's losing energy, which wouldn't happen in the solar system, right? Not noticeably. There's some perturbations from other planets and things, but this one does lose energy and spirals in. If I don't push it as hard, it will do an ellipse for a while. So one of the things I thought of to do with this is when you study the solar system, all the planets are going around the sun the same way. Why is that? Did God decide that he only liked clockwise, or it's like whether it's above or below the solar system, right? Why is everything going in the same direction? Well, the answer is it wasn't. Different directions. But there was a preferred direction. A distant form from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's going the same way. That was 90% of the time. And
So you can find this video on YouTube, I think, but it's a very nice visualization, especially because you see if you have two masses and you don't give a sideways push, as he said, they will be attracted to each other the same way we are attracted to Earth, because space itself is pushing us down. But you don't need that explanation, okay, on everyday life, right? You can use Newton, it's much easier. The equations are much easier. That's what we teach in Physics 1, even algebra based, so it's very easy math. This is very complex math. Okay? So then in 1919, okay, but I will get back to that next time. I want to show you a video, but there was this very famous experiment that was able to show that Einstein was right, that space itself is curved. So it was not a theory anymore, it was a fact. And usually, to wait for a theory to be proven, you have to wait maybe years and hundreds of years. But Einstein, okay, became a rock star from night to day or night to night, day to night, because of that very famous experiment. So they were able to prove that he was right. So I just want to show you a great video that I have found, except I don't know what it's called. Okay, very nice video. Very, very nice. I think we have time. We have just the time. I'm going to speed up a little bit. So it's very nice for the visualization that they use, right, with the computer.
And long before Einstein, the quest for unification began with the most famous accident in the history of science. As the story goes, one day in 1660.
So it's very famous, okay? He's developing a string theory. If you heard about that.
The young man was sitting under a tree when all of a sudden he saw an apple fall from above. And with the fall of that apple, Isaac Newton revolutionized our picture of the universe. In an audacious proposal for his time, Newton proclaimed that the force pulling apples to the ground and the force keeping the moon in orbit around the Earth were actually one and the same. In one fell swoop, Newton unified the heavens and the earth in a single theory he called gravity.
The unification of the celestial with the terrestrial, that the same laws that govern the planets in their motions govern the tides and the falling of fruit here on Earth. It was a fantastic unification of our picture of nature.
Gravity was the first force to be understood scientifically, though three more would eventually follow. And although Newton discovered his law of gravity more than 300 years ago, his equations describing this force make such accurate predictions that we still make use of them today. In fact, scientists needed nothing more than Newton's equations to plot the course of a rocket that landed men on the moon. Yet, there was a problem. While his laws described the strength of gravity with great accuracy, Newton was harboring an embarrassing secret. He had no idea how gravity actually works. For nearly 250 years, scientists were content to look the other way when confronted with this mystery. But in the early 1900s, an unknown clerk working in the Swiss patent office would change all that. While reviewing patent applications, Albert Einstein was also pondering the behavior of light. And little did Einstein know that his musings on light would lead him to solve Newton's mystery of what gravity is. At the age of 26, Einstein made a startling discovery that the velocity of light is a kind of cosmic speed limit, a speed that nothing in the universe can exceed. But no sooner had the young Einstein published his idea than he found himself squaring off with the father of gravity. The trouble was, the idea that nothing can go faster than the speed of light flew in the face of Newton's picture of gravity. To understand this conflict, we have to run a few experiments. And to begin with, let's create a cosmic catastrophe. Imagine that all of a sudden, and without any warning, the sun vaporizes and completely disappears. Now, let's replay that catastrophe and see what effect it would have on the planets according to Newton. Newton's theory predicts that with the destruction of the sun, the planets would immediately fly out of their orbits, careening off into space. In other words, Newton thought that gravity was a force that acts instantaneously across any distance, and so we would immediately feel the effect of the sun's destruction. But Einstein saw a big problem with Newton's theory, a problem that arose from his work with light. Einstein knew light doesn't travel instantaneously. In fact, it takes 8 minutes for the sun's rays to travel the 93 million miles to the Earth. And since he had shown that nothing, not even gravity, can travel faster than light, how could the Earth be released from orbit before the darkness resulting from the sun's disappearance reached our eyes? To the young upstart from the Swiss patent office, anything outrunning light was impossible. And that meant the 250-year-old Newtonian picture of gravity was wrong.
If Newton is wrong, then why do the planets stay up here? Because remember, the triumph of Newton's equations come from the quest to understand the planets and the stars. In particular, the problem of why do the planets have the orbits they do. And with Newton's equations, you can calculate the way that the planets will move. Einstein's got to resolve this dilemma.
In his late 20s, Einstein had to come up with a new picture of the universe in which gravity does not exceed the cosmic speed limit. Still working his day job in the patent office, Einstein embarked on a solitary quest to solve this mystery. After nearly 10 years of racking his brain, he found the answer in a new kind of unification. Einstein came to think of the three dimensions of space and the single dimension of time as bound together in a single fabric of space-time. It was his hope that by understanding the geometry of this four-dimensional fabric of space-time, that he could simply talk about things moving along surfaces in this space-time fabric. Like the surface of a trampoline, this unified fabric is warped and stretched by heavy objects like planets and stars. And it's this warping or curving of spacetime that creates what we feel as gravity. A planet like the Earth is kept in orbit not because the sun reaches out and instantaneously grabs hold of it, as in Newton's theory, but simply because it follows curves in the spatial fabric caused by the sun's presence. So, with this new understanding of gravity, let's rerun the cosmic catastrophe. Let's see what happens now. The sun disappears. The gravitational disturbance that results will form a wave that travels across the spatial fabric in much the same way that a pebble dropped into a pond makes ripples that travel across the surface of the water. So we wouldn't feel a change in our orbit around the sun until this wave reached the Earth. What's more, Einstein calculated that these ripples of gravity travel at exactly the speed of light. And so, with this new approach, Einstein resolved the conflict with Newton over how fast gravity travels. And more than that, Einstein gave the world a new picture for what the force of gravity actually is. It's warps and curves in the fabric of space and time. Einstein called this new picture of gravity general relativity. And within a few short years, Albert Einstein became a household name.
Einstein was like a rock star in his day. He was one of the most widely known and recognizable figures alive. He and perhaps Charlie Chaplin were the reigning kings of the popular media.
People followed his work and they were anticipating because
So it's a very nice video, and you can see here what you see here.
Will form a wave that travels across.
So this is called a gravitational waves, and they were detected recently that led to a Nobel Prize. Okay, so it means you're going to predict here that if you have, for example, two neutron stars, so it's very heavy. Okay, so it's going to bend the fabric a lot. So if they orbit each other, okay, so they're going to lose energy, going to go get closer to each other. They're going to shake the fabric of space-time, and they're going to make those ripples. So that's what Einstein predicted. And only recently, when they got enough, technology, they improved the technology enough, they were able to detect those gravitational waves, right? And that was predicted by Einstein. So I forward 2017. 2015, and that led to a Nobel Prize. 2017, so only 2 years. Sometimes it takes time to get a Nobel Prize, but in that case, it took only 2 years. Okay, so it's quite amazing, the technology that they had developed. And then next time I will talk about the experiment that they did in 1919 to show that Einstein was right, and that's how he became so famous. Okay, he also started quantum physics, modern physics, but that's another story. So we'll talk about that next time.